Open this.
All right, for bell work today, there's a problem here based on the raffle that just came out. There are 6 prizes you can earn for this raffle. If you have 60 points and you decide to put it all on the Fitbit, what are your chances of winning if at the end of the competition, 120 tickets were put towards a Fitbit? Also, what would you actually spend it on if you had a choice? I'll give you 3 minutes.
Who's dying? No.
Yeah, I guess not.
Yeah, go for it. Yeah, what's that about?
You broke it.
Why you break the things, Ian? Oh, I see why. I see why, Ian.
Maybe you didn't realize.
I can't lose. It was in zone. All right, about 1 more minute. 1 more minute.
I don't get like all. Gross. Yeah.
Yeah. Okay, to solve this problem is 2 steps. First step, how many points can you put towards the, or sorry, how many tickets can you put towards the Fitbit? 6, because you have 60 and it costs 10 points each. How would we find out the probability of out of all of those 120 tickets, one of your 6 was chosen? What do we do? You just divide. If you divide that, you'll get 0.05, which is 5%. Also known as a 1 in 20 shot of getting the Fitbit. But what would you actually spend your points on? What do you think the best option is out of these 6? Nobody? I'll tell you what, first and second hour said the Sonic drink was the best choice. Third hour said Fitbit. Panera was the voted least valuable out of all of them. Yeah. So then you have to do this little calculus, right? Where you say, okay, if everyone thinks Sonic drink is the best, then your tickets have less value there, right?
Yeah.
But so maybe you put it all in on the Starbucks because people don't care as much for Starbucks, right? Where you could get, or Panera, where you can get more likely to win. Also, they told me that if you win the fast food lunch brought to you at school, they don't pay for the lunch. What? Is that true? If you win fast food lunch brought to you at school by a principal, they don't pay? The principal doesn't pay?
So who pays?
You. That's what they said. That's third hour though, and they're kind of yahoos there, so I don't know if that's true.
They better be paying.
That's what I said. Mr. Kathy can't put out $15 for lunch?
I want you to pay for it.
That's right. Well, the Sonic drink, I think they pay for. But they thought that you had to buy your own lunch, which is lame.
They'd probably be like, you get one without cheeseburger. You don't even get fries or anything. One
What?
regular cheeseburger.
Plain, no
Plain,
cheese.
yeah.
All right, we have a lot to get through. Maybe. Each individual thing is not that tough, in my opinion. It is a lot at one time. We're going to do this today and tomorrow. And then the homework won't be due till Thursday. So no homework due tomorrow. First thing we're going to talk about are, for this chapter is over sequences, series, and probability. It's probably one of the most real world applicable chapters that you'll take this entire year. First thing we're going to talk about is sequences. A sequence is a set of numbers in order where you can label your numbers like this is the first number in the pattern, second number in the pattern, third, fourth, so on. It could either be infinite and go on forever, or it could be a set of n positive integers. Everyone okay with this definition? And then with this definition, oh, whoa, what is this about? What is this? I have to do it myself? What kind of world do we live in? I have to write in these subscripts myself. All right, so you can write a sequence either explicitly or recursively. An explicit sequence will tell you the nth number in the pattern using a formula. So we could say the first number in the pattern, a sub 1, would be 3 times 1 minus 2. How do you write minus signs like that? Or 1. Is everyone okay with that? We use that explicit formula. The second number in the pattern would be 3 times 2 minus 2 equals, what is that, 6 minus 2? It's 4. The third number in the pattern would be 3 times 3 minus 2, or 7. The fourth number would be 3 times 4 minus 2, or 10. But you could also use this to find the 105th number in the pattern, right? Be 3 times 105 minus 2, which is 313 is the 105th number in the pattern. 1, 4, 7, 10. Can anyone tell me what the 5th number is? What's the 5th number? How'd you get that? Yeah, all that happens is it's plus 3 each time. So another way to write that sequence is to use a recursive definition where you tell me how to get the next number using the previous number. So for this one, you tell me start at 1, and then to get the next number, you just add 3 each time. So here's an example of a recursive sequence. This sequence tells me that the first number is 3. And then to get any other number k in the pattern, you take the previous number, k minus 1, multiply by 2, and add 1. Do you see how we read that? This starts at 1, first number is 3. To get any other number k, you take the previous k minus 1, the last number, times it by 2, and add 1. So for this one, it would be a sub 1 is 3. The second number in the pattern would be 2 times 2 minus 1 plus 1, which is 2 times a sub 1, which is 2 times 3 plus 1, which is 7. That's so messy. Why is it so messy? Who wrote this? That makes sense? Ish? All right, let's do one more. The third number, if we plug in 3 for k, would be 2a 3 minus 1 plus 1. 3 minus 1 is just 2. So I'm going to take the second number in the pattern, which is 7, and I'm going to multiply by 2 and add 1. So the third number is 15. To be honest, though, it's probably harder to write it out than it actually is just to do it in your head. The fourth number is the previous number times 2, 30 plus 1, 31. The next number would be 63, then 127, then 255, and so on and so forth. You just times it by 2 and add 1. Notice that this is pretty nice for getting the first early numbers, but how would we find the 105th number in this pattern? You would have to find all the numbers up to 104, take that number times it 2 by 2 and add 1. So recursive formulas are generally, I feel like, more how your brain actually operates. Like when you saw this pattern 1472, you probably didn't think that the order for this pattern is this formula, but instead thought I just add 3 each time, right? Same thing with here. It's probably easier to think of this pattern as I take the previous number times by 2, add 1, previous number times 2, add 1, previous number times 2, add 1. And that can be pretty useful for understanding how the pattern works, but it's not very useful for finding the 105th number in the pattern. All right, you ready to try some of these? Yeah? Excited? It sounded like you said no, but I can't. You did?
Yeah.
It sounded kind of like it was really like one of those no, but you mean yes kind of things, right?
You're so right. You're like,
It's like, no, let's do this. Like, do I want to get on that roller coaster? No. But do you really want them to encourage you to get on the roller coaster? Wait here, I could do another. Why did it didn't do this for your papers, did it? It just hates me, is what it is. Me and Google Slides, we fight all the time. Okay. Let's do it. How about this? If you're not ready yet, I will start the timer, but after 30 seconds, I'll start doing some of these, okay? But what I'd like you to do is tell me the first 4 terms in each of these patterns, except for the last one, tell me the first 6 terms in that pattern. I'll give you 3 minutes, but I'll start some of these after a 30-second head start if you need help. Oh, gosh. There we go. That's better. The last pattern is a famous pattern. Snails follow this pattern. Also sunflowers.
This is fire.
No,
It's the spinny thing.
it's a spinning thing.
The spinny thing.
Fib,
Fibonacci.
Fibonacci. The last one is the Fibonacci sequence.
Yeah. That's what all the natural things call.
That's right. Most spirals follow the Fibonacci sequence for the lengths of their shell. All right. Do we need more time? No? Are you sure? I'm holding up. I'm going for it. And by I'm going for it, you know who's going for it? I'll tell you who's going for it. Nobody. I'll tell you who's going for it. You want to know who's going for it? Nobody. Still nobody. You know who's going for it? I will tell you who's almost going for it. It was almost Riley. It's John. All right. How do I find, what do I do with this 3? How do I find the third term in this sequence? Yeah, so it's going to be 3 plus -1 to the third power. What's -1 to the third power? So 3 minus 1 is 2. What's the, how do I find the fourth term? What is -1 to the fourth power? Yeah, it's just 1. And 3 plus 1 is? So this pattern is 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, for infinitum. For infinity. Forever. Just going back and forth between 2 and 4. Thanks, John. You know who wants to help with the second one, though? They really wanted to do the first one, but Miles. All right, Miles, how do I find the third number in the sequence? Yeah, plug in, well, 3. Yeah, I already did the first and the second one. All right, so we plug in 3, Fred. -1 to the third power, we talked about that's -1 over, what is that, 5? 6 minus 1? All right, and then what do I do for the fourth term? Just plug in 4? Yeah, same thing, just plug in 4. But -1 to the fourth is now +1, and the denominator becomes 8 minus 1 is 7. So what is this pattern doing? It's switching from negative to positive, negative to positive, negative to positive. And then does anyone see the pattern in the denominator? It's going up by 2. These are all odd numbers. This is a very important explicit sequence, if you want to count by odd numbers, 1, 3, 5, 7, 9, 11, so on and so forth, it's 2n minus 1. That's important. That's like an ACT fact that you just got to know. If you want to count by odd numbers, you use 2n minus 1. All right, thanks, Miles. Next one, 3, 2. Ian, getting both of the Q6 in here. All right, what's the next number in the pattern? 6, 7. Next number is? What's the next number after that? What about after that? How are you getting this? You take the previous k value and you add 1, and that will give you the k plus 1, the next k value. You just add 1 every time. All right, I'll take a volunteer for the Fibonacci sequence. Does anyone have the next term? It's 2, and then it's 3, then 5, then 21, and so on and so forth. How are we getting these numbers?
That was my next question.
You add the previous 2 numbers. To get any number k, you will take the last 2 k values and add them together. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. Did you know that it actually took a bit of time before the creation of the Fibonacci sequence and the explicit formula to find it? Like if we want to know what's the 100th number in the Fibonacci sequence, we really don't want to do this arithmetic 99 times and then get the answer. This is the explicit equation for Fibonacci sequence.
The date 2048 has a Fibonacci sequence.
It's right here. This is the explicit formula to get any number n in the Fibonacci sequence. Yeah, it does look dumb, doesn't it? 1 plus square root of 5 over 2 to the nth power minus 1 times, or minus 1. 1 minus the square root of 5 over 2 to the nth power over the square root of 5. By Jack Benet. That's something different. I think they're related, but yeah, that's something different. Everyone happy with how to use explicit and recursive formulas? So I know what you're thinking now. Well, what if I give you a sequence and ask you to give me the formulas? Would that be fun?
Yeah, that's what I was.
All right, so here's the pattern 1, 3, 5, 7. To write the explicit one is the harder job. Here's what you want to do. Write the numbers. This is my first number, second number, third number, fourth number. How can I get from 1 to 1, 2 to 3, 3 to 5, 4 to 7, and so on and so forth? What do I do to this 4 to get the answer 7? Double it and minus 1 or plus 3. Plus 3 works for this one, but does it work over here? So how do I get from 3 to 5? The same way I would get from 4 to 7. You've got to take your number n, double it, and then subtract 1. 1 times 2 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 3 times 2 is 6, minus 1 is 5. 4 times 2 is 8, minus 1 is 7. Hey, remember I said it's really important? Again, all this pattern is counting your odd numbers. 1, 3, 5, 7, 9, 11, 13, 15, 17, and so forth. This is your formula for that. The recursive one is usually the one people recognize as easier and just have a struggle with the notation. Recursively, how do I get from 3 to 1, 3 to 5, 5 to 7, and so on and so forth. What's happening each time? +2 each time, right? So how to write that in recursive notation is you have to tell me what's the starting number. The first number in the sequence is 1. And then what's the rule? To get any number k, I will take the previous number, k minus 1, and I will add 2 to it. And this is true for all k greater than or equal to 2. Why do we have to start at greater than or equal to 2? Why can k not be 1? Because, yeah, that's right. Because the first number does not follow the rule. The first number is just 1. That's it. That's the start. It gets a special equation. Your rule then will apply to all the numbers after the first number. All numbers, the second term in the sequence and beyond. So this is your explicit formula. And this is your recursive formula. Ooh, gosh, I'm so good at drawing straight lines. Okay. Okay. All right. So let's try this one more time. To get the explicit, again, the first thing we're going to do is we're going to label our numbers. And then I'm going to look for a pattern. How do I get from 1 to 2, 2 to 5, 3 to 10, and 4 to 17? Squared plus 1. You take add, you square it, you add 1. That's pretty quick. Good job, Kyle. That's why we pay you the big bucks. All right, let's do the recursive. Okay, so for the recursive, we're going to start with what number? 2. So for recursive, our first number is 2. How do I get the next number? What is the pattern from one number to the next? This is a hard recursive one. It's actually, this is a hard explicit and recursive one. This is a tough pattern right here. Yeah, there's the pattern. +3, +5, +7. It's adding an odd number each time the odd number is getting bigger. So we'll take the previous number and then we're going to add the odd number. How do you write an odd number in a formula? 2k minus 1. Where k is greater than or equal to 2. Now, does that work? Is that okay? If we plug this in, there'd be 4 minus 1 is 3. Yeah, that works. That's a tough pattern right there. That one's almost easier explicit than it is recursive. Yay? I think it's kind of fun. It's like a different kind of math that we've been doing all semester. Got to work different wrinkles in your brain. Anybody need more time to write? Okay. To be honest, I don't think there's one that asks you like this on the homework. Most of them are like the first one. Try these two. Write an explicit and recursive expression for each pattern. Give you 3 minutes. Again, for the explicit, the first thing you want to do is label your numbers. First number, second number, third, fourth, fifth. First, second, third, fourth, fifth. And then tell me, how do I get from 1 to 1, 2 to 5, 3 to 9, 4 to 13, 5 to 17? How do you get to that? That's actually, I said this was easy. That's actually kind of a tough little problem right there. I'll give you a hint for the first pattern if you're stuck. You will need to multiply it by a number and then subtract a number. So you have to do 1 times something and then minus to get back to 1, 2 times something, minus to get back to 5, 3 times something, minus to get back to 9. If you're not sure what to multiply by, do the recursive first. And the rule in the recursive will tell you what you have to multiply by. All right, I'll give you another minute to check your answer with the neighbor before we go. Look at a neighbor's paper and get help if you need. I also walk around if you would like me to give you a hand. That's right. We're curving. So you gotta tell me what's the starting number, and then how do I get one number? Right, number, what's the
But then
rule?
5 times 4. I don't know the difference. I don't know the difference. 4.
Yeah. Recursive, you tell me how do I get from one number to the next. Explicit tells you how do you get any number n in the sequence.
This is A1, so 1.
All right, let's do the recursive first for this one. What is the first number in the pattern? 1. How do I get the next number? Every time you just plus 4. So I'll take the previous number and I'll plus 4. So if you can actually use that to get the explicit formula, what do you have to multiply 1, 2, 3, 4, and 5 by? 4. And then you'll minus 3. 1 times 4 is 4, minus 1. 2 times 4 is 8, minus 3 is 5. 3 times 4 is 12, minus 3 is 9. 4 times 4 is 16, minus 3 is 13. 5 times 4 is 20, minus 3 is 17. So those are your explicit and your recursive formulas are related. Again, the explicit one we can use to find any number in the pattern. If you want to find the 100th number in this pattern, it is 397. 4 times 100 minus 3. The recursive tells you how to get from one number to the next number. That's telling us that I just take the previous number and I add 4 and I will get the next number. Jay? All right, did anyone get the explicit for this one?
This one, like, that was too complicated. Come on now.
2n plus 1.
Yeah.
Yeah, I did it. Oh.
Yeah.
These are all the odd numbers again, but just we don't start at 1, we start at 3. So this is 2 times 1 plus 1 instead of minus 1 now. If you wanted to start at 5 instead of 3, you would do plus 2 or plus 3, 2n plus 3.
You start at even number with the
So it's
Then you just 2n. You don't have to plus 1. Any number doubled is even. Any number doubled plus 1 is odd.
Oh,
Isn't it cool?
oh.
It's the best stuff.
Let's tell my mom about that.
You should. All right, what's the first number in the sequence?
3.
How do I get the next number? Plus 2. You take the previous number and you add 2. So again, you can use this to find your explicit formula. Do you see how this is a plus 2 here? And a times 2 here, plus 4 here, times 4 here. Those are related. If you're simply adding the same number each time, then to get the formula explicitly, you have to tell me how many times am I adding 4. Right, so I'll take my number times 4. And then you'll just add or subtract to get to your starting number. Yay?
Yeah.
Do I do more of these?
No.
No?
I don't think I'll say.
How do you say no to that? This is like my favorite type of math.
My face gets-
All right, okay. Does anyone need more time to write? All right, last thing we'll do is my favorite operation in math. And that is a factorial. If n is a positive integer, then n factorial is defined as n exclamation mark.
That's what goes at the end of the sentence.
And now it goes after numbers too.
Punctuation.
N exclamation mark tells you to take the numbers 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 till you get to the nth number. And then tell me what that is. As a special case, 0 factorial, 0 exclamation mark is 1. You show that to an algebra 1 student, you'd be like, equals 1, and they'll be like, what?
Like, what?
If you have a surprised 0, it turns into a 1. It's like, ah, and now it's 1. Do you see this?
A surprise 1.
Is also 1.
So what's a surprise 2?
What is a surprise 2?
2.
What's a surprise 3?
6.
Okay, well, hold on, I'm writing. 6 was the answer. What is a surprise 4?
Just do like 1 times 2 times 3 times 4. 24.
Is 24. What's 5 factorial?
5. I can't even do 24 times 5.
24 times 5?
Doesn't like 100.
It's 120. What's 20, 60, 120?
120 times 6 is 720.
Okay, too fast. Yeah, that's 720. Do you see how fast these numbers get really big? How many different ways could you shuffle a deck of 52 cards? 52 factorial.
I saw a crazy.
It is such a huge number, 52 factorial.
Okay, so it was like talking about how if you grabbed a pair of tweezers and like took a single grain of sand from like the Sahara Desert,
Yeah.
and like walked, and then like after grabbed like a dropper and took 1 drop from the Pacific Ocean,
Yeah.
and moved on to the other ones, and then walked around the world like 90 billion times, you would be halfway through 52 factorial or something.
It is such a huge number. It is crazy how big it is. It used to be, I wonder if my calculator can do it.
That's why they say that you can never shuffle a deck of cards the same
Yeah.
way it's been shuffled.
Ever since,
The beginning of time.
if all of us shuffled every second still. It used to be when I taught this class that you would do it in your calculator and it would just say error overflow. It looks like it could do it now. If you want to type these in your calculator, you hit math and then you go to probability and then it's option 4. So it's math and then you go to probability, PRB, which is basically you have to go right 3 times. It's the last column. And then it's option 4, exclamation mark. So if you do 20 factor, nah, that's too big. Let's do 10 factorial. 10 factorial is 3 billion. It's the next button you push. So you hit math and then the 4th column is PRB. So you have to go right 3 times and then exclamation mark. So if you want to test if you're doing it correctly, tell me, type in 10 exclamation mark. You should get that that's 3,628,800. So if I took a deck of cards, okay, and I just counted out 10 cards, 5, 10, and I shuffle these 10 cards, there are 3.6 million different ways that these could be ordered for 10 cards. Isn't that crazy?
That's insane.
If you paint all them black, there's one.
That's true. If there is duplicates, it gets a lot shorter. But if it's 10 unique cards, there are 3,628,800 different ways to order those cards. All right, let's do this. Let's write the first 5 sequences of this and then we'll be done. All right, so the first number in this sequence would be 2 to the first divided by 1 factorial, which is 2 over 1, or 2. The second number would be 2 squared over 2 factorial, which is 4 over 2, which is 2. The third number would be 2 to the third power over 3 factorial, which is 8 over 6. Which is 4/3. Or 1.3 repeating. The fourth number in the sequence would be 2 to the 4th over 4 factorial, which would be 16 over 24, which is what? 0.6 repeating. And then the fifth number would be 2 to the 5th over 5 factorial, which is 32 over 120, which is 0.26 repeating. So as you notice, the 6th number will be even smaller, and then the 7th number will be even smaller. This, as you head to infinity, will head to 0. The denominator becomes larger so much faster than the numerator does. Factorials are super powerful. All right. We'll do this one as bell work tomorrow. And then we're halfway through the lecture. Tomorrow, I'm going to give you a preview of what you get to see tomorrow. Look at these problems.
What is that?
These are the problems that you see on the back of movie math classrooms in college. They show a high-level math classroom in college. They always put these on the board.
That's a funky looking.
You will know how to read those after tomorrow.
That's a funky looking.
What the heck? Why did you know?
You want my supper?
You want to find your
I already.
Oh,
I found the TikTok.
No. The middle not that loose. Not right.
Mr. Lake,
Yo,
what number to the factorial of pose did you have in high school?
of pose,
Pose.
1 factorial. Well,
One?
no, not even 1 factorial. Well, I guess 1 factorial.
One factorial? You have pose?
I am sure. I mean, I have only ever been in a relationship with
I was
2
gonna say,
people.
is your
One
wife your high school
person.
sweetheart?
Sophomore year of high school,
Thought so.
and now 17 years later, here we go.
I'm telling her that
18
you
years
said
later.
she's a hoe.
No, the other one was a hoe.
Oh, okay.
There's one other before her.
Oh, I see.
Why did I record all of that?
What's happening?